Thank you. As mentioned, I'm a consulting engineer at Nokia. So part of my job is visit customers, look at their data center networks, advise them or consult them. So that means I see a lot of data centers, different approaches to different problems. In these slides, I bundled all the ideas that I saw, the best practices of the customers that I see all across Europe. I didn't position any Nokia product positioning. So if you would like to see a bit more detailed Nokia portfolio, we have a booth. You can come and find me. I can show you what products we have and what solutions we have. But today, my presentation is going to be more generic and focusing on best practices. So the agenda is we will look at the legacy data center networks, just a single slide. Then on the second part, we will look at today's data centers, IT clouds, telco clouds. I'll also maybe talk about the GPU backend fabrics. Then I will look at how we interconnect these data centers, depending on if you're an ISP, if you're a data center operator, if you're buying lease line, different connection methods exist, and also type of device you have limits or enables you to realize different use cases. Then lastly, I will talk about the validated designs. So if you look at the legacy data center, they were simple. Bunch of switches, as you see at the center. They are interconnected with each other. They're connecting to servers. Typically, these are layer 2 data centers. Spanning tree protocol, a variety of spanning tree running across them. So we are, as you see, some of the links are pruned because of STP. So we are underutilizing the DC bandwidth. And also, once links change places, we see momentarily swaps. So there are also, of course, advanced STP protocols, RSTP, and there are some improvements. But this STP, any STP variety was not addressing the scale needs and also the fast convergence needs of modern data centers. So this is a layer 2 data center. If you look at the modern data center, we have a bunch of servers, workloads, where we run our OpenStack or Kubernetes clusters or bare metals. They are typically attached to leaf switches, either top of rack switches they're named, or middle of the middle row. They are multi-homed to these leaf switches. All the leaf switches are attached to a spine layer. Spines are the aggregation layer for all switches. This is our data center, but we would like to probably connect it to internet or another data center. Typically, we attach them to PE routers, and in between a PE router and a spine, we have border leaves. Here, I mentioned border leaves. They're not any different than a leaf switch. They're just internet-facing. That's why they're called border leaves. This is a cloud design that we see typically in modern data centers. In this architecture, we realize two protocols, underlay and overlay routing protocols. The green arrows that we see over here represents a routing protocol. Could be ISAS, OSPF, or external BGP. The purpose of this protocol is to exchange loopback addresses between leaf switches. So we will be able to tunnel traffic between leaf switches. Typically, that's VXLAN. Nowadays, we also see some segment routing, SRv6 in data centers, but I think it's a bit of an overkill. But most, 99% of data centers are running on EVP and VXLAN. Like mentioned, we have an underlay routing protocol, ISAS, OSPF, BGP, established on point-to-point links, exchanging loopback addresses. Once we have the loopbacks exchanged, before that, I mentioned we have ISAS, OSPF, or BGP, but typically, external BGP is the widely adopted routing protocol. Why? There are many whys. Those whys are listed in RFC 7938. But if you have a large data center spanning across more than 200 nodes or maybe even 1,000 nodes, ISAS or OSPF may not scale well, but BGP is the protocol that scales well. One of the most important reasons for using BGP is the scale. The second reason for me is using eBGP is compelling reason is blast radius. So if you imagine a link failure, a link flap in a data center, typically if you would be using ISAS or OSPF, all the network would be running SPF calculations, recalculating, and link will be flapping. In case of eBGP, only the spines will run the vector calculations, because in eBGP, the peers are always advertising the routes as next hop self. So everybody knows how to reach to that VTAP, virtual tunnel endpoint address, through the spine, and spine is always the next hop. So since the next hop doesn't change, all the other leaf switches will not have to run any routing calculation except the spines. So that means if a link failure or if there's a failure, the blast radius of a failure doesn't propagate across your 1,000 nodes. They're limited to your spines. Spines runs this routing calculations. That's an advantage for large, very large scale data centers. If you have below 100 nodes, it's fine to run ISAS or OSPF. So this is for underlay routing. But I mentioned eBGP is great for scale and blast radius and many other reasons, but configuring it is hard. We have to do point-to-point alignment of AS numbers, neighbor IPs, whatnot. It doesn't have auto-discovery. BGP doesn't have auto-discovery by nature. But then RFC 8950 comes into play. This RFC defines how we can announce IPv4 addresses through IPv6 interfaces. Then we combine this RFC, we call this feature unnumbered peering. So we basically combine this feature with leveraging IPv6 neighbor discovery protocol. So in a sense, we do not assign any IP address on the links. We use IPv6 link local addresses, auto-generated. And IPv6 has a native feature called neighbor discovery protocol. So basically they send router advertisements to their peers. It's kind of like LLDP, but operating in a layer 3 mode. So basically nodes exchanging their interface IPs. So we take the interface IPs using native IPv6, link local IPv6 neighbor discovery protocol. Then we don't need to assign IP addresses and align them because it's link locals. Combining all of these brings us an auto-discovery function for BGP. So basically, we don't assign IPs, we don't assign neighbor IPs, we just align the autonomous system numbers, which can be a range. Then our spine leaf fabric, claw fabric can auto-discover each other like ISAs and OSPF can do. So this greatly enables the easy configuration for our underlay networking. So once we have the underlay routing, we can exchange loopback addresses over this network. Then once we have the loopbacks, we leverage BGP EVPN address family for the overlay routes. So to enable distributed layer 3 networks, stretch layer 2 domains, anycast gateways and whatnot. So EVPN is a Swiss army knife of a protocol. One protocol can do layer 2 services, layer 3, anycast gateways, ARP suppression. We can now even nowadays carry multicast. We can route multicast traffic over EVPN overlay. So overall, if you look at our data center, we are only running one protocol, BGP, with two families, IPv4 address family to exchange loopbacks, and EVPN address family to exchange overlay routes. EVPN is loop-free by design. Split horizon is built into its behavior, so there's no need to run spanning tree or any variety of it. It brings ARP suppression. So basically, we can enable proxy ARP at the access level, and then instead of flooding ARP traffic, we propagate it through the EVPN control plane. So that's no more flooding. Microsegmentation with group-based policy. So basically, we can create, let's say, security groups, microsegmentation groups, and announce these groups, let's say group blue, group red, group yellow. We can propagate this information in the EVPN control plane. And then instead of creating multiple access ACL lists to police microsegment traffic, then we only create a single ACL to police traffic between these groups. But then this information is shared through the EVPN control plane. EVPN comes with standardized multi-homing, no multi-chassis lag or proprietary protocols. We can put a Nokia box and Arista box next to each other. They will do multi-homing. And also EVPN, typically with multi-chassis lag, we would need an inter-chassis link between leaf switches. That would be a waste of a port. In an EVPN scenario, you don't need an inter-chassis link. As you can see, there's no links required between leaf switches. Another EVPN use case, another benefit is host mobility. If you have a container, if you have a VM moving across different leaf switches, you don't rely on MAC learning anymore to determine the next location of that VM or container. Basically, EVPN has host mobility standards that immediately when the host is detected on another leaf, EVPN overlay is updated. And lastly, the multicast, optimized inter-subnet multicast protocol, the feature. It's a new one. So basically, we are able to carry multicast traffic in our data center in an overlay. That means that our spines doesn't need to be aware of multicast traffic or anything. So it's just our network is PIM free. So basically, all traffic is switched between leaves through VXLAN tunnels, and spines are only doing IP routing. They're kind of dummy in a rough sense. So in these networks, for leaf roles, we need devices with an ASIC that can do VXLAN encapsulation, decapsulation. So it requires some more functions. It should be doing routing. It should be doing quality of service or access ACLs, but it should be also cost effective. So these boxes typically get replaced every 2, 3, 4 years, 5 years, 2, 3 years typically. But so typically for leaf roles, Broadcom Trident family is positioned, Trident 3, Trident 4. For spine roles, they're more dummy devices. They just do pure IP routing. They require high number of ports and high throughput. Typically, we position their Tomahawk family from Broadcom because there's not much functionality needed and they're quite low latency. We also position Tomahawks for AI GPU backend fabrics. So I'm talking here about IT fabrics or telco clouds, but in GPU backend networks, there is no EVPN overlay typically. It's just pure IP routing. The requirement is great load balancing and super high throughput and super low latency. That's another use case, but typically we also position their Tomahawk 5 typically. For border leaves, it's another story. We will look at the border leaf cases, what type of boxes that are positioned based on the required functionality. So we talked about underlay routing, overlay routing, the services. If we have let's say we have the network, we have some servers and workloads talking to each other through an EVPN-based VRF. This is the orange one that you see. These VRFs can be multi-homed. So from your server point of view, you have a link aggregation group that you can stretch a layer 2 domain over this layer 3 network. Or you can also have anycast gateways. So you can have a single gateway address stretched across multiple different locations. You may want to extend your VRF network to outside of your data center. Typically, you extend these VRFs on your border leaves. You can have another VRF on your PE router, and then you can do a VLAN handoff. So the red arrows that you see over there are VLANs, and the orange dotted lines are the VXLAN tunnels, and spines are routing those VXLAN packets. So this is the disaggregated case, where the border leaf can be also low function, kind of low cost device, where it terminates a VXLAN tunnel, decapsulates the VXLAN, and gives the packet to a PE router with a VLAN header. And then PE also takes this VLAN and then encapsulates it into MPLS or SRv6. So in this case, the data center and the PE, they are decoupled. That works for some customers because their data center network team and their wide array network teams are different. They typically don't like each other. They always finger point at each other. So they love having a VLAN in between so they can easily pinpoint which team's responsibility is the outage or the problem that they have. But this requires coordination. You have to align VLAN addresses. And also, if you stretch, for example, pure layer 2, you rely on MAC learning to detect failures. You don't have a protocol in between. Typically, the convergence is slower if it's pure layer 2. Some customers we see, their whole network team is united, data center network and wide array network. They typically prefer extending this VRF, EVPN-based VRF, also on the P router. In this case, there's no need for a border leaf. They can typically attach the P router to the spine and then stitch the EVPN-based VRF to an IPVPN-based VRF logically on the P router. That eliminates the border leaf, but you need a bit more sophisticated P router, an ASIC that can stitch VXLAN to an MPLS. Typically there we see Broadcom Jericho-based platforms or Nokia's FP-based platforms. So if you look at the data center, let's look at the data center interconnects. We shuffle the same boxes in a different way. Here we see the leaf switches on the bottom, spine in the middle, border leaf again, and the P router at the top. It's the same design from a different angle. That was my data center one on the left, and I have an identical data center on the right. Now, we will look at the gateway-based DCI, decoupled. I talked about it a bit. So this is the case where the data planes are decoupled. So we have a VRF from the leaf to the border leaves. Then we have another VRF on the P routers, and then we have VLAN handoff. It creates decoupled data planes, different teams managing data center and one. No special ASIC hardware required. The limitation is you cannot do end-to-end. You cannot take benefits of end-to-end EVPN. You have basically different EVPN domains in different data centers, and you have to align IP addressing. You cannot do host mobility, and basically you don't take advantage of much of EVPN. But it's easy, and cheaper boxes can do that. We have an integrated model of the same, where we just collapsed the PE router and the border leaf into a DC gateway, a single device. We got rid of the border leaves. Some vendors also call these DC gateways as border routers. They require to be either Broadcom Jericho or Nokia FP-based platforms, because you need to be able to stitch tunnels. You need to be able to make multiple lookups on the same turn inside the chip. So that requires a bit more high-end chip. But that brings us some advantages. Basically, you don't, in the decoupled case, if you had a layer 3 network, you would need to do option A between these two VRFs. You need to align. If you have 1 or 2 or 3 VRFs that you need to do option A, it's fine. But if you have hundreds of VRFs that serving to other commercial clients, that requires a lot of peerings needs to be established between these VRFs in the decoupled mode. Once we collapse these two together, you don't need to establish an option A between border leaf and the P gateway, because a single service, we can stitch both domains together and leak routes as you like. You can apply quality of service here and then access control lists. So basically, DC gateway merges these two domains, stitches. The limitation is you cannot still stretch EVPN across data centers, because data center 1 is in another EVPN domain, data center 2 is another EVPN domain. They are interconnected through an MPLS or SRv6 tunnel, but then one EVPN update on data center 1 is not propagated on data center 2. Let's say host mobility. Then, if this is not a problem, this is a great use case. But there are also other options. Interdomain option B is one of the approaches. In this case, This is based on the draft interdomain option B. We are operating one big multi-site data center. EVPN updates are propagated back and forth, and basically the DC gateways are in a role of ASPR. They are basically rewriting the next hop to themselves. So typically what happens is EVPN data center 1, here we see encapsulates the traffic on a VNI 1, let's say. The ASPR swaps this label, VNI to MPLS or SRv6, propagates it to the 1, and then on the other side of the 1, same thing happens, next hop self. So these DC gateways keep record of which route is in which domain and which routes to announce itself as next hop self. Data center 1 sees all data center 2 routes as next hop DC. This brings some advantages. So basically, there is no service instantiation required on the gateways. Gateways are just doing label swap, VNI to MPLS, pop push, or vice versa. Also, it eliminates the next hop scale pressure. So if from a leaf data center 1 leaf point of view, normally all the next hops on the other data center would be a different next hop. That would be a different VXLAN tunnel or a different tunnel. That would eat out from the fib entries that you can populate as a next hop. You can use it as a next hop. And typically these leaf devices, they are not the most high-end chips. They are Trident. They have quite low scale. If you're looking at a data center of thousands of nodes, a Trident chip cannot have thousands of next hop tunnels. So that creates a next hop scale pressure because we are now operating our data centers in one big domain. Then every next hop has to be installed in the fib. This eliminates that. Basically, data center gateway rewrites itself and announces itself as the next hop. From a leaf point of view, all data center 2 next hops are next hop data center 1. So we basically eat out from one next hop tunnel address. Disadvantages: once we propagate EVPN routes across data centers, the route targets and route distinguishers can be translated back and forth, but you lose the BGP route attributes. If you're doing, if you're announcing communities, your communities will be lost in between. We basically do label translation and that's it. It has advantages, but it doesn't solve all problems, depending on what problems we have. Disadvantages is, yes, like I said, no translation of route attributes. And this only works if the wide area network is MPLS, because we do MPLS label swap. You can have MPLS, SRMPLS, MPLS over IP tunneling, but no SRv6. So you have to have MPLS over here. And still, the leaf point of view, the next hop amount drops because next hop will be the data center gateway, but still it has to keep all these MAC and IP addresses of all data centers in its fib. That's quite a large number. Sometimes leaves cannot handle that many routes. Still a scaling issue on the leaf side. Then we have a solution for that, service gateway solution. In this case, it's a similar design, but we instantiate a VRF on the data center gateway or the router. What do is they import and process the route. They install the prefix in the fib, either IP prefix, MAC address, tags, keeps the communities. Then it allocates a demultiplexer for the next domain encapsulation. So data center gateway does import the route, translate it, and serves it to the next domain. So it just redistributes the same route into the next domain. That requires a sophisticated chipset, like typically Jericho or FP4, FP5. Advantages is you don't have encapsulation restrictions. You can have you can have SRv6 in one data center, translate it into MPLS, and in your other data center you may have EVPN VXLAN, basically using VNIs. If two companies merge and if they have different data plane approaches, and they have to now make those workloads talk to each other, this is a great option. There is no VPN next hop scale pressure because again, DC gateway announces for all the other routes, remote routes, it announces itself as next hop self. So basically leaf switches see the DC gateway as the next hop for most of the routes. In this case, the translation of all VPN route attributes are done. If you have special communities, if you're executing actions on based on that, communities and all the attributes are translated and propagated between data centers. Basically, you can operate multiple data centers with full EVPN feature set. You can stretch layer 2s across. You can distribute a gateway between data centers. You can have ARP suppression, broadcast boom traffic suppression across data centers without any limitations. The disadvantages, you need to instantiate. First of all, you need a capable device as a border router that alleviates a lot of scale problems from the leaves. But you need to instantiate a VRF on the DC gateway that will do the double lookups and translate the routes and announce them to the next domain. The FIB scale for MAC and IP address is still there because if from a leaf switch point of view, if you have 10 data centers with thousands of different nodes, it has to keep all the MAC or IP addresses in its FIB. But there is a catch. DC gateways can announce a default route for this domain. So basically, if the route is not locally known in your data center, it will match the default route and next hop data center gateway. And DC gateway will take care of that. If it knows wherever is that IP address, it will just tunnel it there. Same thing for MAC address. There is a feature called unknown unicast destination. So if the MAC address is not locally known in a data center, the next hop will be pointed to the data center gateway. So basically, the leaf device is alleviated from all of its problems. The next hop VTAP scale pressure is gone. Data center gateway is taking care of that. The FIB scale, the IP scale problems are gone because the data center gateways can announce a default MAC or default IP address. So basically, with this approach, you have capable DC gateways, but quite low cost leaf boxes and spine boxes that you don't need to worry too much about the scaling problems because most of the sophisticated functionality will be on the DC gateways. You can swap your leaves and you can operate thousands of leaf devices as a single EVPN domain and move your workloads without any worry using this approach. I talked about a lot of things, but hands-on is the best way to learn. We in Nokia create a lot of labs for each other. We share them in GitHubs for our colleagues. You can deploy them or run them in GitHub code spaces. You can basically, if you have a GitHub account, I believe you most of do, just click on this running code spaces and it will instantiate you the labs that we pre-built, pre-configured. Then you can just start playing in SSH and discover. Nokia also has validated designs. There are designs for AI fabrics. There are designs for EVPN VXLAN data centers, all pre-configured. You don't have to do anything. In a matter of seconds, you can just instantiate a lab. You don't need a license. You don't need an image. All of our SR Linux images are on the GitHub. So basically, in 5 minutes, you don't need to even talk to any Nokia representative. You can deploy a lab as well. If you would like to deploy multi-vendor labs, we have also a tool that Container Lab, probably heard. Arista is also using that. It was a Nokia in-house project, but now it's an open source public lab tool. We also have the very same labs that we share on GitHub. You can deploy them on your Linux server using Container Lab. Here's one example is the multi-vendor EVPN. If you would like to test Nokia, Arista, Juniper boxes of different kinds in the same EVPN domain, all pre-configured, you can basically do git pull, Container Lab deploy with 2 commands. Lab is ready to play. And with that, thank you.